All right, so chapter 19 is about first-class functions. What do we mean by first-class functions? Well, first-class functions is basically the idea that the functions can be, passed around just like data. Now, what is a function? We know we can define a function, and function is a code. Now, keep in mind that code is also part of your program. And although the code is not modified at runtime, but the code is still, accessed for during the runtime. So the functions that represent blocks of code, if they can be used just like the data variables, then this is really just means that you are making the functions, sort of a first-class citizens of the language. And that's actually what the standard allows you to do, by the way. And so that is what we're going to talk about in this lecture. So first of all, let's start from the basic. So we are aware there's a function pointers, right? Function pointers, this is sort of a feature carried over from C. So it's a little not very intuitive the way the function pointers are defined. So here's a general syntax. Because the pointer has to carry the information about the sort of the function signature, so to speak. And so you gotta have the return type, then you also have the parameter types. And then you want to put the pointer name in this together with this asterisk in a parentheses. This parentheses is very necessary because if you don't add the parentheses, then this asterisk could be considered as part of the return type. So that's why you have the parentheses here. So here's a simple example. Say we have a function called find a maximum value in an array. So this is the function declaration. And then we want to, so first we declare or actually define a function pointer that is able to point to the function of this type of signature, with the return type. These are the parameter types. And then we initialize it with this function that we just declared. So that is fine. This function pointer can take that, is able to point to that type of function. Now, so this, in the case where you're making a variable out of an existing function, and this function pointer, you can actually just use the auto to allow the compiler to deduct the type for you, because typing this out is kind of long. So you can use auto here. Now you can also use auto asterisk. They are the same thing. Now with asterisk here, you're indicating this is actually a pointer. So probably this is a little more preferred way if you're dealing with the function pointers. Now, early on, we'll talk about, in general, you should not be using the raw pointers. And that also goes with the function pointers too. And so there are actually better alternatives. And before we get to the alternatives, actually, let's take a look at the, function pointer. What is the primary usage of a function pointer? You use function pointers typically as the function parameters. You pass, the function pointer around. This essentially allows you to capture a piece of behavior and then allow you to a function take in a piece of behavior that's defined elsewhere to implement the behavior that you want. So in a way, this is actually also similar to when if you recall, we talk about the template method design pattern, where we use the OOP technique to have sort of multiple, so have this class hierarchy where you allow the consumer of your class to customize some steps of a particular algorithm. And so that's really what the template method is about. Now, alternatively, what you could have done if you're not using OOP, if you're just doing sort of structure programming, and then you just use functions, and then this would be the way to do it. You pass a function pointer into your, sort of the template method function, and that function pointer allows, sort of certain steps of your algorithm to be customized by passing that behavior in, those custom steps into your function through the function pointer parameters. So there is an example here in the book to find the optimum value in a vector of values. And so you take a vector of values. This is sort of where you're looking for the the optimal value, basically. And then what is the definition of optimal value, right? So that is defined by this compare function pointer. So we allow the user of this function to pass in a custom compare function. So this pointer points to a compare function that will basically define what this optimum means. And so we can take a look at the code. For example, this is, and so there's a couple of enhancements that I've made. So basically the idea is you're trying to look for the optimal value in a vector, sort of a collection of values. So number one, you see this parameter is a function pointer, which is pretty long and tedious to write. And it's kind of makes it a little hard to understand what this is about. So to make the intention clear, so it's actually preferable to use a alias template. So the alias template, so essentially you have seen a sort of type alias before. If let's ignore this template line for a second, and essentially you can use this using statement, and then you give it a name, and then on the right hand side of this assignment is basically a type name, the type name of a function pointer in this case. So we remove the pointer name, right? But you still need the asterisk with the parentheses. So this is how it looks. So, and then because we allow different types in the parameters, so we can make this, turn this into a template. And of course, this template line with the parameter list, this is just like what you have seen with the function template or class template is the same thing. So we're just using this here, and this now becomes an alias template. And this will be used to instantiate usage of this comparison alias type at runtime, or at a compile time. It depends on what this T will be. So the compiler will figure out the places where you're using. For example, well, here actually we're using this inside another template. So when this template find optimum function gets instantiated with a specific type parameter, and that type will be used to also instantiate this comparison alias template as well. Okay. So that's one. And this looks much better. Now you're looking at, okay, now we're passing this comparison type, which is actually a function pointer type right here. And then the other thing I want to just kind of quickly point out So many examples in this chapter are about returning a raw pointer. The intention is essentially avoid copying to return a pointer that points to an element in that vector. That basically that pointer points to the optimal value inside the vector. Now, so again, so the principle we'll talk about, try to avoid raw pointers. And so instead, what you can do though, because we're trying to find an element in a vector without copy, we don't want to copy, or want to just because maybe this object T is kind of expensive to copy. And so that's kind of there's an alternative way. So this, we know a vector has an index. All these elements they are consecutively assigned, arranged just like an array. And so you can actually just essentially figure out what the index is, much like a string as well, right? So what's the index? And by using the index, okay, that points to the optimal value, and that's very cheap to return an index, right? So if we're worried about performance, so to speak. So then, the index, that's how do you represent when you cannot find optimal value? That's a possibility. What if it somehow can't find it? So in that situation, so you may, sometimes you do find it, sometimes you don't. The case that you do not find an optimal value would be, say, this vector is empty, right? If it's empty, there's no value, so there's no optimal value. And then in the case of a pointer, raw pointer, you can return a null pointer. So what you do here is, okay, and then I can't return a valid index because there's no elements in the vector. And then you use optional. Remember our vocabulary type, optional. That's precisely the case where you want to use optional, because you may have a missing value. You may not return a index in the case where this vector is empty. So I just want to point this out. You can look at this. It's very clear the way you see it. This is actually, I would say, better than the raw pointer solution here. Okay, just want to point this out. But we're going to continue discussing and looking at other examples that's going to use the raw pointer. But that's not the main point of this chapter when we talk about first-class functions. Okay. Now, a better option is called where you can use a function objects. So we're moving toward, again, OOP techniques, right? So essentially, so many things that we do with this whole language is trying to push us into using the proper OOP techniques, all this idioms and stuff is, because it's just more powerful. So let's use function objects. What are function objects? By the way, there's a nickname for function objects. Sometimes it's just shortened as a functors. Function with objects sometimes it's called a functors. So they are interchangeable. So what is a function object? A function object is an object that can be called as if it were a function, right? So if you got an object, and then you can call that using this object, like you call a function. So let's see a simple example. So we've got a class less, and this actually the less has a single member function here. This member function is a overload of this operator. This with the parentheses here. We'll talk about the function overloading, and so actually we'll probably actually mention the function operator overloading as well. So this really, if you have this function, this class could have many other things just as a normal class could. If it contains a overloaded function call operator, that means this can be considered as a function object class, right? So if you make an object of this class, then this would be the function objects. So if you make an object of less, and then this less, you can use that just like a function name. You can call this, provide these parameters because this function call operator is overloaded. Okay. And of course, there are a lot of the thing we just talked about, the less, it's already in the standard library. So you don't need to write a function object class like that. Instead, if you encounter the standard, most of the standard operators, like comparison operators, arithmetic, logical, and bitwise, all these operations, these operators, they have the equivalent. We already have the equivalent standard function object classes defined. So what this allows you to do, though, is basically allow you to even extract out if you want to use a operator, in the case where they say we'll try to find optimum, and then we let the user define what optimum is. It could be less than, could it be greater than, right? And then you can just pass in a function object, and by using this standard function objects, then you allow the user to customize the behavior of your function, or could it be a class template, whatever that you're trying to do. But your function is going to take a function object as a parameter. And just a little bit about the less in the standard, the way to use this is just all this standard function objects that the way you use them, you don't really have to specify the template parameters when you're using them, because the type can be deduced by the compiler. The reason that can be done, this is the kind of technique here, just kind of show you what, okay, how is that achieved? You may do something for your own class templates. Now, this we using the struct here because the I just don't want to type this public here, so because the members are by default public. Just remember structures are have the same capability as classes, so they all basically the same stuff. Now, so you have this class template, right? For less, it deals with you can pass in different types, and then what we do here is we specialize is an explicit specialization of the template, and we'll talk about specialization. So this is the full explicit specialization of this template because there's only one parameter, and this is for the case of void. Okay, so void type. Now, because it takes a void type, because there's no need to use this. So it's not even used here because the reason is we're actually defining for the function overload, the function operator overloading, that itself is a function template. So what this allows you to do is the compiler is instructed to deduce the parameters you pass into this function call. When you make a function object out of the less, the compiler can deduce the types you pass into the parameters, and then that way, basically, if you're doing that, you're actually not using the parameter at the top. You're just kind of making a function template essentially. Then you wrap this in a class. That's what you're doing. So if you don't specify the parameters in the angle bracket, that means that's because there's a default value defined for that type parameter, which is void. And then so when that is the default, so then basically it's going to pick this particular function template. This is a class template, and so this is the specialization that's going to be picked to basically that will be picked for that particular function object usage. This goes with all the other standard function operators, right? And then there's a third way of specifying first-class functions. That's called the Lambda expressions. Now, if you look at this, really the whole point of that is really the whole thing is about the function. Well, but of course, this is a class. You can actually obviously can take parameters, so to the constructor if you want, and the text have a member variables, right? And so this is a simple example. It doesn't really store any member variable. So essentially, your function objects can have a state that can again. So this whole function objects, there's a better way to express that. It's a more concise way. That would be the lambda expressions. So lambda expression, what is it? It's an expression. This expression, well, what it will do is it give you a closure object. What is a closure? A closure is an unnamed function object. See, it's kind of, the whole point is to make a function object. It is capable of capturing variables in scope. Now, it's unnamed function object because not like less here. This is obviously named. This is what we're doing here. In the case of a lambda expression, so let's take a look at some examples. This is the general format, so I'm not going to explain too much about the format. So basically, it starts with square brackets. That is the capture list. Now, the capture list can be empty, but you still need that square bracket. This stars, syntactically, it stars that lambda expression. And then over here, the angle bracket, these are the template parameters. So yeah, so the lambda expression could be templates. And then the text parameters, just like a function parameters. And then you have some specifiers. An example specifier would be mutable. Later, I'll explain what a mutable will do. And then you may also obviously have a no except, the exception specifier. So could it be a no except if that is what you want to do? Then you may also specify a return type. So the return type is not really in front and is in the end. So this is called a training return type. Okay, so with this arrow here, you could use this training return type with the regular functions as well, but it's just not very commonly used and is unnecessary. Now here is kind of necessary because the way the syntax of this lambda expression here, it doesn't really, because it doesn't have a name, right? So it's kind of unnamed situation. So this is kind of a out of necessity, this whole return type is moved to the end. Now the return type can be ignored. If you don't have it, then you're asking the compiler to deduce it. And it will deduce that based on your function body, your return statement in your function, in that lambda body, just like a function body, by the way. So you see a lot of similarity with the function, but of course there's no function name. This is a lambda expression. And the end result of the expression is it's going to generate a function object of some kind of unknown class. And that class definition, that will be generated by the compiler. So the simplest lambda expression is like this. You have a empty capture list. Then you have an empty body. And in the case of having no parameters, and you can ignore that whole thing here. You don't have parameters and that can be ignored. So this would be the simplest. It's empty. Obviously, it does nothing. So you can invoke this, of course, with no parameters. So you invoke this with like empty, parentheses. That's it. But of course, it does nothing. It's no op. And then here's another example here. And then we see this takes two parameters, integers, and it has a return statement in the body. So this is essentially comparing x with y to see if the x is greater than y. So based on this expression, by the way, the compiler is going to deduce the return type will be basically a Boolean. And then here is a lambda expression it's called a generic lambda, and it's just like because it's using a template and template argument parameters, just like a function template or class template or alias template. And now you see this thing with a lambda expression as well, because we're trying to generalize the parameter types. And so here's an example of this trailing return type. If we do want to specify the return type explicitly, say we want a bool, and that is fine. Sometimes you do want sort of precise definition, that there for various different reasons. But again, you may or may not have it. Whether you want the compiler to deduce it. Sometimes most time probably you want the compiler to deduce it. If it doesn't give you what you want, maybe you want to have the return type specified. And this is lambda expression. Now we only finished half of it. Now the other thing is we've seen this capture list. Why is this always empty, right? So what can you do with this? What is capture list? So the capture list is basically allows the lambda expression to capture, so-called capture, the outside of variables. So the variables that are in scope, this lambda at the location of lambda expression that you can access. And then you want to access those variables inside your lambda function body. So let's take a look at what you can do. There's a couple of examples. So you can capture all the outside variables by value by using this equal sign in the square brackets. And so when you capture values, so basically it's doing a copy, right? So it will not just supply all the variables that you can, access, but it will simply the end result of this, the compiler is going to generate a class definition, right? Just like a function object class, it will do something like that equivalently, but also it will going to provide the variables that you're capturing, you actually have used in the body. The variables you're not using in the body, they're not going to be captured, basically. So this does allow you to capture anything that you want that you can access in the scope. And of course, but this is by copy method. So we'll pass those variables into the underlying function object in terms of the basically essentially we'll have like a constructor that will take those outside of variables by value. Okay, so there's a by value, and then we know there's also by reference. So by reference, you essentially just use this ampersand symbol here. That means now you can access all the variables you can access through a reference. Okay. Now, when you capture by value, by the way, all these variables inside the lambda, even though they are a copy, you're still not allowed to modify them. And if you do want to modify those variables for some reason, then you should use that specify here, and this will be basically use the mutable keyword. Now, we have some mutable somewhere else, right? So remember in the member variables of a class, if you have a constant member function where you cannot modify your member variables, but if you want to prevent exception to certain member variables, then you use a mutable keyword in front of the member variable definition. And so here that you can give an exception to access the variables you copied if you want to modify them. And then by the way, you're modifying a copy. You're not modifying anything that's outside because you retrieve the copy. So now if you capture the variables by reference, of course you can modify them. That's kind of the main purpose of that anyway. Now you can have a mixture of both. So what you do is you first to say, here's my default capture method. This is by value. And then we have some variables that we do use, we want to reference by, want to capture by reference. And then you do this way. So this X and Y they're captured by reference, everything else by value. And you can do the opposite also, like say capture everything by reference, but then X and Y, they are by value. But well, keep in mind here, we're not using the equal sign here, just a regular variable, as if you would, declare a variable without any symbol. But anyway, this is just a syntax. So X, Y this is by value. Everything else by reference. So what happens if you're using the Lambda expression inside the member function, and then you want to access the members of that class? Well, you can capture this pointer. So then you just use the keyword this in the square brackets. Well, remember, actually, you can still you can mix this pointer capture with the other types that we explained before. So this is one extra thing you can capture, and this is a special case. So this is a special case. So when you do want to capture this pointer, and you capture this way, okay? Now, when you do capture this way with this is a capturing this pointer by reference. So inside the Lambda expression though, then you don't really need to use this pointer to access the members. And then basically it gives you the same access as any member function. In a member function, you can access all the private members, right? Private member functions or private member variables, all those things you can access inside this Lambda here. Of course, you're using that inside another member function. And then you can also capture this pointer by value. Now, what does that mean? That means you are making a copy of the current object. Then you are doing something inside Lambda with that. So with this asterisk before this, now this is the syntax. Don't read too much into this, but this helps you really remember what you're doing here. So anyway, this is to capture by value, making a copy of the current object. So these are the various different capture methods. And so let's actually take a quick look at it, see if we have an example here. Lambda. Okay. Let's see. Okay, so here's an example. So remember that find optimum where we pass this compare. So this find optimum is still taking this comparison type. Now, actually, right here, we're actually just elevating that comparison type into a template parameter. So that's fine. This allows you to pass whatever you need to pass. So here, what we're doing is we're passing that Lambda expression. And this Lambda expression results in we know is unnamed function object. And then inside here, this find optimum template function, and then we are calling this compare like a function, right? So we know this function object from Lambda expression, that closure object, essentially the better name for that is called a closure object. That is obviously, just working like a function. You can invoke that, and so that is not a problem. So this is and as you see, it takes two parameters, X and Y, in double type here. And then it does some kind of comparison. It returns the comparison result. Basically, this will give you a Boolean return type. And so exactly basically what this can do here, this is just showing by this comparison here. Now, you may also have noticed that, okay, this Lambda is, takes double So what this essentially means here is when this is provided some other value, let's say they're not double, essentially what the compiler will do, essentially, if let's say they're integers, and this is a vector of integer values, then they will be converted, implicitly converted to double to invoke that compare this closure object from this lambda expression here, okay? So it's not a problem. I mean, if the compiler fails to convert, then we'll report an error. That means, okay, it's not compatible. Now, so over here, as you see, we are using this optimum is we're taking just a type parameter here for this function template. And we're not really saying what this is, right? It's like, this could be anything. What if this is an integer? Like if it's an integer, then of course you cannot invoke an integer like this, right? So if you want to be more specific to say, what this type should be, I want this to be a function-like entity or a first-class function, essentially. Could it be a function pointer? It could be a lambda expression, a closure object or a function object. How do you enable that, right? If you want to be able to take all of them and also saying this is what you want that to be a callable, something that's like a function. And this has no restriction, no constraints here whatsoever, right? So to make that intention clear, what you can do is use this standard function class. Now, this function class itself is also a function object class. So a function object, this standard function class, when you make an object out of this, it can store, what it can do is it can store, copy, move, and invoke any kind of function-like entities. So it's like a wrapper around. What this is essentially a wrapper around a function pointers or function objects or lambda closures or whatever they may be, as long as they can be invoked like a function, okay? And so the general form of this is it's a function, it's actually a class template, right? It takes some arguments, and this argument is a little unusual. Parameters, sorry. The parameters are a little unusual for this class template, and then you see it captures the return type with the parentheses and then a list of parameter types. And here's an example. This is how you may write it. Yeah, so it's almost like simulating, specifying the almost the function signature, right? So you're saying the return type is bool, and takes two parameters. They're both integers. And so, so we'll make an object of this function class. And this object can take, you can actually assign, all these different types of a first class function objects or pointers to this object of the type of function, because this is, it's compatible. It's got sort of the member function defined to take care of those situations. And here's the other thing. It allows the implicit conversions. If, as long as the parameters can be converted to ints, and then the return type could be converted to bool, and then it works. It will take it, okay? So then if you think about this situation, what you really want is probably better to pass this function type, right? And then it will make it real clear this parameter for this function has to be a function-like entity. So this is the alternative way of doing it. And then you're able to essentially specify more details on your template, what this is supposed to be about. Okay. So of course, if you actually do use that function type here, if I'm using this somehow passing a type that's incompatible, it's not a function-like entity, then there will be a compile type error. That's actually what we want, right? Okay. We're going to actually look at an example of usage of this as well in a design pattern. Now we have introduced a template method design pattern before, and here's another design pattern. It's called the observer. So what is the observer design pattern? So the intent of this design pattern is to define a one-to-many dependency, okay, between objects, so that when one object changes the state, all its dependents are notified, notified and updated automatically. Now, this may look a little sounds a little familiar because if you have dealt with some kind of a GUI type of application, maybe a web application, using JavaScript, you deal with the situation of a typical pattern where you have the data, which is also called the model. And then when that data changes, you want to change what you display to the user. That's also called a view. So this, that type of relationship. So when something changes, you want to notify some other component in your program. And that is really what this observer pattern is about. And let's take a look at a class diagram here. So what you have, primarily, you have a subject. So the subject is it holds the important state. Like when we talk about the data, if that data changes, it will notify all the observers. The observers are the other component that's basically will be called upon. When it doesn't notify, it will call this update function on the observers, and the observers are attached to the subject through this attach method, attach function here on the subject. So the subject is going to maintain a list of observers, because every time an observer is attached to the subject, then it will add on to this list of observers. And then when it gets the time to notify because something changes and then they are interested in, and then it will essentially just call all the observers update update function. And then of course in the update, it will do something interesting or whatever. Maybe it changes the UI, display a dialogue now where I show an error message or whatever. And then you can probably, the way this is sort of an interface level, and then you make a concrete classes that to basically implement this pattern of subject observer pattern. And there are alternative terminology we actually can call. Sometimes you've probably heard about, more familiar with, pub sub model, right? This is the subject is the publisher and the observer is the subscriber, right? The subscriber subscribes to a publisher. That's kind of the other terms that you may have heard of. And so how does it look in code? So there's an example code that actually just illustrates the observer pattern. So we have this observer interface. Now this is interface because it only contains pure virtual functions. Well, in addition to of course, you always should have a virtual destructor here. So this is an interface, and it has this update. It also uses has a member function that's called the getID. So using the ID to identify the observer. So here we're just saying this ID is a number, it's a size type. And then the subject has this attach, detach, and notify, just like what we saw in the diagram here. And this is also a interface. Now here, this attach. So the attach takes actually an observer ID as well as a update callback. So I'll show you an example here, what this is, how we're using this function, the standard function class here. So the function class, what we're using here is we're going to take, a function like entity that can be called with a string view parameter, and it doesn't return anything. And that is describing actually this update method of observer, right? So this update takes a string view, here, well, we're just not doing much interesting. We're just taking a string. In a real application, you probably take other objects that have some kind of importance to the application. So the idea is that we're going to remember these callback functions. Now, this callback function is going to hold on to a sort of a member. It's going to hold on to a member function. It's not a free function, but a member function. Let's see how this might be used. Let's take a look at the subject. Let's say we have a concrete implementation here. So when you attach, and then we're going to put this observer along with the ID into a map. So we're using a map container. We're going to actually study STL, the standard template library. We have used a lot of vectors and arrays, and this is another type of a container. It's called a map. A map allows you to store key value pairs. Fairly simple to use. It's just like you use it almost like any other container. So because we want to remember ID, we use this. The ID becomes the key. And then to detach, you essentially erase that ID out of that map. So that's the kind of the most interesting thing here. And then let's look at the observer, the update. So when we do an update, remember this is going to be sort of called. Okay, let's actually look at one more thing first. I'll explain this a little bit here. And so this is we're using. So when we instantiate an observer object, we want to attach to a subject at the same time. But of course, in real application, you don't necessarily have to do that. This is an example here. Let's say when you need to attach at the time of constructing observer object, and then so we're going to attach it itself to the subject, right? So we pass a ID, and now we have actually a static counter to count the ID of this observer objects. And and then we use this actually the bind function is a standard function bind. What this allows you to do is to bind this is actually the member function called update from observer. It will bind this member function with this object. This is actually the current object of this observer itself. This is the current object we're trying to bind. And then have a placeholder here. And this is saying, because remember this update takes a one parameter. And so this parameter, we're just, this is we're deferring. We're not specifying that. Essentially, this is saying we're not making the function call yet. We're doing a binding here so that in the future, this can be called when this object of observer is constructed. So we're deferring. This kind of is necessary to do here because we're constructing this object observer is not done yet, right? This pointer is not even complete at this point. So, but this bind allows you to defer the function call for later. So we're saying if you do want to call this, function update um, from this attach, right? Remember this attach will have this update callback. This is the callback. This bind is a function-like entity. It gives a callback to the attach function, right? And this essentially gives exactly that, but we don't necessarily have a complete object here yet. And then and it's also specifying we have a placeholder parameter. And this is really what this bind allows you to do. Okay, so this is a maybe a little bit advanced here, but kind of just know this is a one way to do it. And actually, in this situation, this is one of the probably the proper ways to do it. And then we have a test program here, and we're going to basically make a subject, and then we'll make a bunch of observer, initialize it with a subject. Essentially, they will be attached to those subjects, right? And then we create a message on the subject. When you create a message on the subject, what it will do is, let's take a look at this. It will remember that message, and then we'll do the notify. It will notify the observer, hey, I got a new message, So this notify, the notify will do is first it will print out the observer count, how many observers. This is just for debugging purposes. And then essentially what it will do is it will look through these observers and then send them the message, right? So remember, this observer actually is the function callback. Well, the second argument, the second means is the value. Remember, it's a map. So the key is the first one is the ID, and the second one is the callback. So here we're actually invoking that callback object with the message, with the message argument. And we also know that callback here is, where we bind, it's going to be just simply calling the update. Calling the update function on the observer. Okay, so that's essentially this is what this is what gets called. So let's actually run this. So first, well, I already compiled this thing, but I can just show you again. It will probably say up to date. All right, that took a while. So I'm gonna just run this program here. So you actually see those all these CL statements to print out some messages. So this is making these observers 1, 2, 3, and then we send a message. Send a message, then it prints out. Okay, we got 3 observers. That's the count. And then remember that notify is going to notify all the 3 observers. They're all going to say, well, we got a new message, and the message is, hello world. Okay. And then we detach observer 3. So observer 3 is removed. And then we send another message. The weather is hot today. So then, there are 2 observers in the list, and then send the message to these 2 observers. Okay. And so on. It's the same stuff that goes on. Okay. So that's really an example of observer design pattern. It's very useful design pattern. Sometime in your programming life, you're going to encounter something like this. So hopefully that helps. And let's go back to the slides. And let's kind of summarize quickly. So first of all, we started with a function pointer. That's sort of a carryover feature from C, and you don't really want to use that in a modern C++ program. But you need to be aware at least a function pointer stores the address of a function. And then what you really want to use typically would be called function objects. This sort of, again, this OOP would go into the OOP techniques. Now, function objects are objects that behave like a function. And then the way to make it is essentially you're overloading the function call operator. That's what makes a class a function object class. A function object can have member variables. Of course, it's a normal class, right? Only difference is now you have overloaded the function call operator. And then the concise way of making a function object, also writing the code if the code is short, you want to use a Lambda expression. And usually another advantage of Lambda expression is you're writing that piece of code where it is needed. And suppose it's not being reused in many different places. If it's getting reused in many different places, maybe you want to define a function class, object class. But otherwise, for ad hoc usage of many places, especially when you're working with the containers, you'll notice that you're going to use Lambda expression quite a bit. So it's a very concise way of defining a function object. The compiler is going to actually generate something of the equivalent to a function object class. It has a name, but that name we cannot access. And then the variables captured by the value, they are by default non-modifiable in a Lambda. So if you do want to modify them, you want to use the mutable specifier that goes after the that specifier you want to add to the right after the parameter list. So the training return type of Lambda is actually optional. If you don't specify that, the return type is deduced. And then you may want to think about using this function class, the standard function class, to specify a function parameter if you want to accept any first class functions. So that's an example that I've just shown you with the observer design pattern. So that's all. Thank you.